Good evening, everyone. I'm Shah. I'm currently a PhD student over here at Arizona State University, and I'll be presenting for today's workshop about convolution neural networks. We'll start from the basics of what a convolution means and what does a really convolution neural networks look like, and maybe we'll end towards the implementation of a CNN. Yeah. So before I get started, I'll just quickly say a few words about me and how has been my experience in deep learning so far. So I started off my undergraduate college at DISD in India in Gandhinagar, towards which in my second summer internship I did over at Singapore NTU University, which was the first point I learned more about CNNs and what CNNs look like and what goes into the mathematical framework of building a CNN. Followed to that, I worked as an intern and also a full timer for a very brief amount of time at HackerRank, where I developed challenges that are typically used for people who are getting started into programming and in order to crack their interview tests. And I worked over there as a machine learning engineer. After which I graduated out of my undergraduate degree in information and communication technology. After which I joined ASU over here for my master's program, and I got an opportunity to work with Professor Frank Wilczek, who is also a Nobel laureate in physics. And I over there, my experience of building augmenting senses using deep learning was one of the biggest factors that I learned a lot over here. And working with him was something very differently challenging. Experience for me because I learned many aspects of deep learning and how deep learning can be really creative about domains like physics. After which I joined Philips as a research and development intern, where I again used many of the video detection algorithms, which are commonly used for person detection, person recognition, face recognition. And being an R&D intern, I really got to work on some of the very cool technologies which are normally not even used in the day-to-day life because they are highly patented over them. And I got a brief introduction of what deep learning can really look like and how much robust it is. After which I graduated from my master's program and I joined over here at ASU in my PhD program over here recently in 2020. Currently, I'm working in cross collaborations with Mayo Clinic and Banner Health on various medical imaging projects, where again, I'm using deep learning as a tool to understand how we can really develop biomarkers in diseases like Alzheimer's, migraine, and many other post-traumatic headaches. Apart from this, I maintain a YouTube channel where I post contents and I interview people who have been really working nicely and who have been really making great progress into understanding how machine learning really is and how you can get started. And I post contents with people, I interview people about their journey and how they got started and what they really feel about this domain. On this side, I also volunteer at two organizations, which are IEEE and its children organization, which is called the IES, which is Industry Application Society, where I collaborate and I volunteer as a chapters and membership development program, where we organize conferences, where we organize paper submissions, and we review articles. Also, I'm the technical director for AI Club since almost more than a year. Yeah, more than a year now, and it has been great. I help organize the team technical workshops, just like this one being of them. And also, I host a podcast series where I create content from the interviews that I conduct and I talk to people, and I have some insights about how you can get started and what are the commonly asked questions about the confusions regarding deep learning or in general machine learning. Okay, so and you can visit my website in just in case if anybody wants to reach out to me for any other specific doubts. But I'll get started with the today's workshop that is on the CNN. Just for a brief agenda of what it will look like, I'll start over with an introduction of what CNNs are, followed by which we'll talk about the architecture overview of how CNNs look like, how they work, and what are the typical components of convolution neural networks, which consist of layers, many different layers over here. And by the end, we'll switch to a demonstration of how you can get started and how we can build one of the simplest CNN algorithms using a framework called TensorFlow, which is one of the most easiest frameworks available out there, provided by Google, where students can really build CNNs in just few minutes. So that would be what the agenda for this workshop would be. But feel free to stop me over at any place or any slide, just in case if I'm moving too fast, or if you have any questions that you want them to be answered. I'll love if I get interrupted, and I'll love to have a discussion with during the presentation too. So feel free to unmute yourself and ask me any questions. Okay, so starting about the CNNs. Um, just a very quick introduction of what really convolutional neural network is. It is one of the most highly mature developed feed-forward ANN, which is artificial neural network, and they are typically termed as connet. So wherever the codes you would see online, they always use connet terms, which is typically a convolutional neural network. And the idea of using convolutional neural network was to utilize the 2D image structure of an image. So that is where you will see CNNs are typically used in image and videos and not in tabular format data. So over here, as you can see on the image, the right-hand side of the image is a much more tabular format data where you would see column-wise data, the one that we store in Excel, CSVs, and all those files. But CNNs are not useful because there is no amount of spatial information that is being really recorded over here. So these are row-wise data, what we say. But images are much more spatially interconnected. So each of these pixels really mean a lot in its surroundings. So connets were really developed to utilize that particular information and use deep learning on top of that. So a normal connet is normally like this is the ideal framework of how connets really look like. They have some amount of convolutional layers followed by a pooling step. And we'll talk about what these pooling steps mean and what are these interconnected layers looking like. So coming to the architecture. So to understand how convolutional neural networks work, we should also understand how the motivation and what is the motivation behind design of such a complicated but yet very elegant design of connets. Consider an image that is of the typical size of 200 cross 200 cross 3. And to understand what these mean over here is an image which is of the size 200 pixels wide, 200 pixels heighted, and it has 3 channels, which is what we normally say RGB channels, which is the red, green, and blue channels over here. Before convnets, there was a term that we normally use is called the MLP, the multi-layer perceptron networks. And over there, we have these connections from each of these input channels to each of these neurons. But because we see these kind of high dimensional data, which is 200 cross 200 cross 3, if they are connected to each of these neurons, they really increase the complexity and the computation cost for each of these particular computations. But how ConvNet really elegantly designed this particular framework was to reduce this computational load and yet again increase the efficiency for that particular classifications. So typically in convolutional neural networks, what you will find is the layers are connected only to a specific region of the particular image in every computations and not to the whole image. And in a way, they are trying to understand what the patterns look like. They are trying to see which are the common repetitions of patterns instead of just putting whole image into the network at a time. So this is what it normally MLPs versus convnet difference looks like. As you can see on the image on the left, we have these inputs connected to each of these neurons in the hidden layers. And you can see the number of connections increase. And you can imagine the input to be of the size 200 cross 200 cross 3, which is a very fairly small amount of image size. And you can just imagine the number of connections that you can find in between these layers, which is huge in terms of computations. But how convnets really define these things is a typical example. It looks like this. You can create these small buckets of connections where you can see only these two neurons are connected to these particular hidden layer neurons, and so on and so forth. So you can see the kind of reduction in the computations, and yet we will later on see how this design really is more efficient than the existing MLPs. So this is what in reality it looks like. You can denote by any of these two methodologies, and you will see on the internet or any other places where they term coordinates. The architecture looks something like this over here. So we have the input layer, which refers to the input. They are typically videos or images, and we have these hidden layers which are a part of the convolution neural network, which we as programmers or we as computer science engineers will design. And we have a particular label over here. We label this particular image being a cat or a dog, which refers or which resides into the output layer. And a connet normally arranges all of these filters, which we will see feature maps in a three-dimensional manner, because each of these images in today's world we see they are colored images, so they have a basic minimum channel size of 3, which is the RGB. Okay, we had a very quick overview of what architecture looks like. Now let's deep dive into what exactly each of these components of a particular convolutional neural network looks like. So just starting off with a very basic example, just imagine a particular image where you want to classify if this normally refers to the alphabet X or an O, which is normally a normal character from the tic-tac-toe game. And we want to classify if that particular image refers to X or O. And just a very brief understanding of image, how if a zoomed in image of X would look like over here, it looks like this particular image on the bottom. And we want to develop a particular CNN model that can say, hey, this image belongs to X or maybe O. Now, to an computer, these are just black and white pixels. They don't really understand what this particular pattern means, but we as visually, we have the ability of perception. So we can say very quickly within a matter of second that this is X. But let's see what content really sees like, and why. To understand why convolutional neural networks are important is if we understand some of the difficult cases. Now we can see these four images, and we as humans can really see that, hey, these are X's. They are just maybe translated, maybe scaled by some version, or maybe rotated. But to a particular computer, these things might seem very different. So in order to develop a CNN that is really robust to all of these particular cases, so that it is not tricked by certain kind of variations, uh, these are normally which convolutional neural network says trickier cases, but design of convolutional neural network really handles these cases very easily. And similarly for O, you can see these images are highly different. So you have to develop some kind of architecture that is robust to any kind of variations in images. So just to understand what is the difference looking like, if I rotate the X over here by a slightly tilted angle, this is what image would look like. But to a computer, this is a completely different image, and it would say, hey, this is not an X. Then how do we say, how do I define convolutional neural network to understand that this is just a slightly tilted version of an X? Since the pattern doesn't match over here, so as you can see, there is a pattern where we can see a diagonal elements of a submatrix really are aligned over in a diagonal fashion. But over here we can see there are no pattern matchings. There are x's at different places, so computer wouldn't be able to see that this is an X. Now coming to understand why, this was a typical example of why computers were not able to classify images very correctly before convolutional neural networks. Now coming to I'll just quickly say a few components about the convolutional neural networks in order to proceed with these examples. We'll be talking about four particularly highly consistent components of a convolutional neural network. First being convolution layers, followed by ReLU layers, followed by pooling layers, and finally fully connected layers. I'll talk about each of them very briefly in the subsequent slides. So coming back to the original problem that I discussed just a few seconds back. So to understand what really got changed over here, to understand we had these diagonal elements, but something changed and hence the computer was not able to see this particular pattern. But what a connet really is good at is it doesn't see over here. It doesn't see each of these pixels at a time, but rather it takes each of these small components over here and it tries to match if it can find that particular component in the output image. So we can see this is the original image of X, which was perfectly aligned, perfectly fine and beautiful. But this was a slightly tilted version. But what convolution neural network does is it takes these kind of small patterns over here, which we will later see these are called filters, or maybe they are said learnable weights in certain terminologies. And it tries to find if these kind of filters are really found in the output images. And as you can see, at least from a very basic understanding of human eye, we can at least see three or maybe four types of patterns that are being repeated. The central image over here, central image over here, these small patterns are really matching. So this is what convolution neural network looks for in iterations of deep learning training. And it tries to see if it can find a complete match of this particular patterns, even by a certain amount of percentage. So I just mentioned a term called filters. What are these filters? What does this filter means? In order to understand these kind of small, in order to understand these kind of small subset of patterns, it has to learn over a time. Over here, it was me who mentioned that these kind of diagonal white elements and diagonal black elements is a filter. But in a convnet, the convnet has to learn on its own. So these are what typically a edge detection filters might look like. But over here, these values are provided by me, or maybe the paper who came out over here. But the convnet has to really learn these filters. So that's why I say over here, these are learnable filters. And these learnable parameters are really learned over subsequent amount of data inputs and training over iterations. So this is what you will always find these words, which are called forward pass, which is normally the forward pass of a particular training, where you feed in the input and you try to match that particular input to the output. And more precisely, we will talk about how these forward passes consist of convolutions, or the normal grammatical term that we say convolve, that is combining each of these filters of each of these pixels of the filters and the images. I know this is too much, but let's see a graphical version of what it looks like over here. We slide these filters over the images, which we term as in the whole of the computation as a convolution. So what does it look like? Let's say this is the filter over here and with some random values, but for the sake of simplicity, I have given these values ones and minus ones, where ones refers to white pixels and minus one refers to the contradictory, that is the black pixels. We try to superimpose these particular 9 pixels over the 9 pixels of the image, and we try to do a simple element-wise multiplication. So this is what it would look like. Let's say, just before I move on, I'll okay. Let me, yeah. Yeah, this is what a normal convolution neural network would look like. Let's say we superimpose this particular filter on the first section of the image, and we try to do a simple element-wise multiplication. So, and then we move on to the next pixel and so on. And it goes on throughout the whole row-wise fashion, and followed by it goes down and so on. And how does this element-wise multiplication mean over here? Let's say these pixels are really superimposed on this particular section of the image. We try to multiply element-wise. We try to do an element-wise multiplication over here. So one cross one, it's one, and so on and so on. We find at least these 9 elements, and I won't go through, like, this is fairly easy, so I won't be repeating each of these numbers, but I'll just quickly go over these slides to make you understand. And we go on over here for all of these 9 pixels. This is what a normal one step of convolution really looks like at one particular region of the image. And to take on the average values of this pixel, this is a function that we denote for the sake of simplicity. Let's say these are 9 values and divided by the total number of pixels in this particular subsection. And we denote that this particular value is 1. So this is the output, which is called the feature map, which is the output of a convolution by applying filter over a certain section or patch of an image, and so on and so forth. So I'll just quickly take a second example over here. Let's say the filter over here was sliding over all of these pixels and it came to the very central of the image. So what the output looks like, we just keep on multiplying these values and we see there are 2 minus ones included. And we again take the average and we denote this particular value over here as 0.55. So on and so forth. So I guess you guys get the pattern of how convolution really looks like. And we pass on this particular filter for the whole of the patches of the images. So it moves throughout all of these rows and throughout all of these columns. And we get filled on this particular whole matrix that we will be calling feature map. So this is what it would look like. So if I applied this particular filter over all the values of the pixels, it would generate certain amount of values for each of these particular boxes, or we say feature maps, the cells of these feature maps. And one thing that if somebody would have noticed over here is the input was a 9x9 image, and at the output we got a 7x7 image. That was because over here we are using this particular filter and we are applying it to the very left of the corner. So we are missing out on certain amount of values on the border, and hence we are only considering the central regions starting from over here, from this one to over here. So it reduces this particular images to a 7 cross dimension size. But we don't have to worry about that right now. Why the image really shrunk in size? But to understand, these are the values, these are the outputs of what one iteration or one multiplication of convolution really look like. But let's take it to the next step. Why just stop over here? So if I applied this particular filter to this particular image, I got this feature map. But what if I did this particular filter? It would produce a different feature map, and so on. So we can see these are the size of pixels, these are the size of filters, and we have using stride. I'll come to the stride in just a moment over here. So this is what the output looks like. We apply these filters. We can apply 2 or 3 filters. It really depends on how many filters we want to use. And in case if I'm using 3 filters, these are the 3 channel outputs that I'm really getting at each of these convolutions. Now coming to the stride, let me just go back over here to understand what stride really means. So sliding over these pixels. So over here in the example that I showed, if you can notice, if you really notice over here, I'm just moving 1 pixel at a time. So the next step is moving the box just 1 pixel at a time. This is what we will say stride. If stride equals to 1, that means I'm shifting these particular filters over the image one pixel at a time. But at times you will also see stride size equals to 2. That means I'll be just skipping these convolutions by 2. So if I started over from the very left corner, I'll be just moving to the second corner and a size of 2. This is what stride really means. But as of now, we don't have to worry about that, because that's just something you will figure out in the design of how the convolution neural network looks like. Now, coming to the particular normalization layer, I'll come to the pooling layer after the ReLU. It's just a typo on my slides. Normally, pooling layers are applied after ReLU. So we'll talk about ReLU layers first. And what ReLU is one of the very popularly used normalization layers. So if you did notice over here, you see a lot of negative values and a lot of positive values. Now, negative values are really bad when you are trying to train your convolution neural network, because negative values really become big in case of backpropagation. So we have to get rid of these negative values in order for the model to really behave nicely and not very drastically. So because negative values will be really amplified by a huge number, so model might end up learning something wrong. So we try to minimize these negative values. So what ReLU is a very complicated name, but what it does is something very simple. I know the name really sounds highly complex, rectified linear units, but what it's really doing is it's just converting each of these values. So let's say if it's a 0.77, so it's a positive number. So ReLU says, hey, I'll just keep it 0.77. But let's say I received a minus 0.11, it just converts it to 0. So anything that is less than 0, it just terms each of them as 0. So it just converts all of these negative values into a static number 0, but it keeps the positive values as it is. So over here, you can see all the positive values remain the same, but we convert these negative values to a 0 number. and so forth. So we convert this particular feature map into this particular updated feature map after the normalization layer. This is what normalization means. Normalization is just a fact checking thing that convolutional neural network designers did because they saw that in order to get rid of these negative values, we can just simply cut them off to a particular static value 0. So right now we had three feature maps over that in the example. After the ReLU layers, you can see each of these values being 0, where the negative values were present over here. This is what ReLU layers really does. Coming to the pooling layer, as I promised, normally we use pooling layers in order to reduce the size of the image that are really redundant. So I'll give an example of what a pooling layer it does is, but to keep in mind is it is just downsampling that particular image in order to save the amount of computations. We are not looking at information loss. We are just minimizing the pattern matching finding algorithms in order to save computations. So let's see what pooling really does is, let's say over here, I'll have filter sizes over here, but these are not learnable parameters over here. Filters are fixed. They know what to do and they have these dimensions. So just for the sake of simplicity, let's say I am defining a pooling filter, which is of the size 2 cross 2. So over here, let's say these are the, this is the particular filter that I'm applying over here, and it will try to find the maximum of these 4 values. So over here, what we can see, the maximum value is 1. So this is just doing a max value, and it is trying to max out the particular values in particular window of the filter. And as I mentioned, we talked about stride size 1 before, but what does stride 2 mean over here? So stride 2 means is I'll be skipping over 1 pixel, but I'll be jumping by a size. I'll make a jump of size 2. So you can see, you can expect what it would look like. The next jump would jump these particular pixels, but it will directly go over here. And again, it will try to find a maximum over here. So it's 0.33 and so on and so forth. I won't be going through each of them because they are pretty straightforward. So they will be just trying to find the maximum values in particular window of range and so on and so forth. So this is what it really does. So this is what the output looks like. Those, and in a way, you can say that this particular image is the downsampled size of a particular feature map that we had. And as you can see, it's pretty easy to guess that it is reducing the dimension of a particular image, but still it retains the pattern of information that you can see. Just to see in a very naive manner, you can see these white diagonals over here in a left leaning fashion. Same you can see over here in a left leaning fashion, but in a smaller image and rest of the information. So you can see the patterns are preserved, but we see a smaller image size over here. And so on and so forth. We had 3 feature maps after the ReLU layers. We performed convolutions, we performed normalization, and we performed ReLU layers. And now we perform the final pooling layers. So similarly, it does for each of these, and we have 3 feature maps being generated. So as of now, we have talked about these particular 3 layers that we talked about. We had the input image of X converted into binary format. We applied convolutions by which we got a pattern matching feature map, after which we eliminated all the negative values, which was the ReLU function, after which we did the max out function in order to downsample. So we applied 3 layers if you remember correctly, we applied these 3 layers to get this particular output. Now, this combination of layers is a typical building block of convolution neural network. When somebody says, I'm building a convolution neural networks, it is set of these 3 layers that they really design and they really vary in order to build a convolution neural network. So to remember, what does a convnet really consist of? It consists of convolution layers, ReLU layers, pooling layers in general. But again, this is the most generally used method, but there are definitely lots of variations depending on the type of input and the type of application that we are using. And to give a better understanding of what it looks like is you have an input sample over here. We perform convolution with certain amount of filters. It changes the number of feature maps that we have. Let's say we had three, which refers to the RGB channels. We apply convolution neural networks with certain amount of filters. If you remember over here, we had three filters that we used in the starting. But let's say I'm using 64, then I would be getting an output of 64 filters with a channel size of 64, and so on and so forth. I'll be performing pooling and all those things. And as I mentioned, these are the typical building blocks of a convolution neural networks, but we can stack them up. We can stack each of these blocks on top of each other. So convolution followed by ReLU, then again followed by convolutions, and so on and so forth. We do this repeated type of pattern matching thing in order to find out the refined layers of patterns, because not all the images are as simple as just finding an X. Convolutional neural networks are now able to find emotions. So they're trying to find face recognition. So they are trying to find much more detailed information into the images, and hence you can see each of these layers really stack on each other in order to find these particular informations. Now, talking about the last layer of a convolution neural network, which is called fully connected layer. Fully connected relay is one of the most simplest layers for any one of us to understand. It just tries to map each of these feature map values into a one-dimensional array. So over here, if you remember, we had this particular values as the final output of after performing certain amount of connet blocks. So what does the one-dimensional array looks like? We can just plot them out in a very snake kind of manner, and we kind of find out a one-dimensional array of each of these outputs. And what it does is it tries to convert these one-dimensional arrays, and it tries to map to the target values. So over here, we had the target as being the image being X or being O. So we try to map each of these values to a particular target. And as you can see, these values denote the probability values of mapping of each of these pixels to a particular target value. So you can see we just sum up these values and say if the value is greater than 0.95, then maybe classify it as X, or maybe if it is not, then classify it as O. So it is a simple classification methodology. So in total, what did we see over here? We had the input image with pixelated values. We applied a set of convolution blocks where each of these convolution layers that we defined over here, followed by ReLU functions, convolutions, pooling, and followed by fully connected layers, we map each of these values to its particular target values, X and O. And this is what we had in mind, that we wanted to classify if it belongs as an X or O. But to keep few things in mind, you might ask is how does a convolution neural network that is being really good at finding X and O's are also good at finding cats versus dogs, or different breeds of dogs. It is not just specific to the type of animal, but also breeds of animals. These are the knobs that I say, which is normally termed as hyperparameters. I really refer to them as knobs of a particular connet that you design, because these are the knobs that you really design in order to make your connet work in a certain kind of manner versus how your friend or somebody else might do it. So these are the hyperparameters that one needs to understand in order to build a connet structure. We don't need to understand all the mathematics behind it, because it might be too much at a very quick intro level. But if you understand the role of each of these hyperparameters look like, you can easily make a connet just at your using your computer. And if you understand what differences or what changes it makes to the output of a connet by tuning, or maybe just changing the knobs of these particular hyperparameters, you can really see what connets really can do great terms for you. And before I jump to the demo, I just wanted to do a quick hands-on over here as to, does anybody has any kind of question regarding the architecture or theory behind convolutional neural networks. I'll be jumping to the demo. So if somebody has some questions regarding the slides or what did that step mean, please let me know. I'll just
I
give.
have a question.
Yeah.
You regarded each of these iterations as a convolution block, but
Mhm.
doesn't seem like there's a specific order. I thought it would go through the convolution step and then the ReLU step and then it will go to pooling, but it seems like there is no specific order. And why is that?
So over here, as you can, let me go to a previous slide. So over here, as you can see, normally convolutions are always followed by ReLU because we are trying to minimize these particular values and we want to eliminate each of these negative values. But pooling is normally applied when in order to downsample and finally do a reduction in the size of images. But if, like I said, each of there is definitely not a pattern of when to use pooling. It really defines. I can use pooling over here too, but if I want to really retain the information after my first layer of convolution, I can choose not to do a pooling. But like I said, it's really dependent on the designer or the programmer how he or she wants it. But this is what a complete block of convolution really normally looks like, where we have convolutions, ReLU followed by pooling, and then we have a fully connected layer at the end. But you can choose to do a pooling or not do a pooling because there is no learning happening over here. We are just doing it for the sake of reduced computations over here. Does that answer your question?
Yeah, I got it.
Yeah. Do we have any other question? All right. I'll jump to the demonstration over here. Let me figure out. All right. Can you guys all see my demonstration page over here?
Yep.
Okay. Okay. So I'll post the link to this particular collab just in case if somebody is on the computer and if they want to try out in the chat over here. So this should be pretty much accessible to anyone who is using a Chrome, using a Google account. Um, let me see. Okay. I'll post the collab link over here so that people can do a hands-on just while I'm speaking over here. But I'll also do a quick demonstration on the screen also just in case somebody doesn't have the access to running these things. So over here, what are we really trying to do? We are trying to develop a convolution neural networks using a API that is normally typically developed and handled by Google, which is the Keras API that was developed as a part of open source project a few years back. And we will be using Keras API in order to build these particular blocks that we just discussed the theory about and what it really looks like. So uh, not to confuse anything, this particular image I have taken it from the internet just in order to visualize. This is not the convolution neural network we will be building, but it would look much similar to what it looks over here, where we have the input layer, we have the convolution layer, we had the pulling layers, followed by a certain pattern of each of these blocks, followed by fully connected layers connected to the final output. And for the sake of this demonstration, I'll be using an openly used data set called CIFAR images, which is one of the most clean data sets available out there, which has around 60,000 images for 10 classes of objects. And these are the 10 classes of objects that they have labeled and collected. One can find is they are, I guess, they are animals, they are vehicles, there are, yeah, these are the two types of images. And within each of these categories they have sub images. So within a bird you will have various types of birds, not just one type of bird. You will have all types of uh, birds within that. Similarly for cat and automobiles. So these the reason I'm using this particular data set, and what I'll also suggest anyone getting started for the first time, is because working with real life data set really makes a lot of troubles. But these are some of the most clean images available out there and highly nicely labeled. So we will be using CIFAR 10 data set just for the sake of simplicity. And as they have mentioned on the website, these images are 32 cross 32 images dimension size with 3 channels as in the RGB. You can see these images are colored images. So they have a by default size of 3 channels over here. Okay, now coming to the frameworks. We'll be using a TensorFlow as a framework, which is TensorFlow, which is a framework offered by Google in order to develop or maybe work with deep learning models. So this is what it normally looks like. So for the people who are for the first time using TensorFlow, we normally connect. It's easy to use because anybody with a Google account should be able to uh, use this particular notebook. But let me know, or maybe any one of our officers can also help. You can post it in the chat section if you are not able to open this in a tablet or maybe in a computer. But everybody should be able to open this thing. And you can see that the runtime that we are using. Google offers a normal CPU based runtime, a GPU based runtime, and also a TPU based runtime, which is one of the most latest developed hardwares that they have available for the common people. We'll be using GPU for the sake because we are not doing anything really load intensive over here. And this is what a normal API really looks like. How do we start off? I'll be going each of these codes line by line, but I assume some certain amount of proficiency with programming from each one of you. So we'll be using certain amount of frameworks where we import the related libraries just in order to get started. We use TensorFlow and its APIs of Keras using, and we use data sets, layers, and models in order to use those functions that they have already implemented. So in order to do that, I'll just quickly hit the run button. So this is what it will do. It tried to import each of these values. And now coming to the data set, we need to download these data sets from the publicly available website over here, which is maintained as an open source project. So we try to label each of these values as in the train images, train labels, test images, and test labels, which refers to the images in training size, training labels, test, and similarly it goes as a straightforward method. And we normalize, you might notice this particular section, we normalize each of these images and in a 0 to 1 between as a value of between 0 to 1. These methods are normally used in order to make sure each of these images fall into a certain region. So images that have a high intensity value on a certain section is not highly weighted in order to classify them. So we perform these normalization techniques in order to make sure these images are on a standard scale. I'll just go ahead and click the run button and it tries to download these images. It will just take a few couple of seconds. And as you can see, the command line shows we can download these data sets from the website. And in order to verify and in order to see what this data set really looks like, we already know from this website that there are 10 classes of images over here. So we label, for the sake of visualization, we label these are the class names. And using a plot function using matplotlib values, we try to plot these images of what they are really looking like. So I'll go ahead and click the run button in order to see what it looks like. So as you can see, I have labeled I have pulled out these images from the data set of maybe more than 60,000, I guess, values or 60,000 images. And you can see these images as frog, trucks, deer, automobiles, and all those particular section. I've just pulled out the first 25 images randomly. And you can see each of these particular values. This horse is much different than this horse, but they still denote the same class level as in the animal horse. Coming to the building of a convolutional base over here. So One of the beautiful things about using Keras as an API is it's really straightforward to build a particular block of convolution in just few amount of lines. So that's why I say over here, just using 6 lines of codes, you can really build a convolutional neural network. And thanks to these APIs available out there, I have this links over here. So anyone with this should be able to find much more details about these con2D methods or maybe max pooling. But they refer to the same thing that we discussed in the presentation previous to this, is using a 2D convolutional neural network and a 2D max pooling layers in order to build the convolutional neural network. So over here, I'll sequential model refers to the feed-forward neural networks that we typically talk about or maybe use, where we have a forward pass followed by a backward propagation algorithm in order to learn and update these parameters. So we define the model as a sequential model using this particular line, and then we keep on adding these layers. So as you can see, as I mentioned over here, these images are 32 cross 32 size images, colored images. So we assume they have 3 channels and size 32 cross 32. So in order to define these layers, we define number of filters. Now again, I have used this number based on my understanding of what CIFAR dataset looks like, but this number would be a very trial and error number that any one of us designing convolutional neural network for the first time should be able to come up with. But for the sake of understanding, I defined 32 filters over here of size 3 cross 3. So if you remember from the presentation, I had these 3 cross 3 filters that I was convolving over each of these images. So this is what it really means. I have 32 of them of size 3 cross 3. I'm using activation as in ReLU, and input images are of the size 32 cross 32 and 3 channels referring to the RGB. There we have the first layer of convolutional neural network. Followed by them, we have max pooling, which is of size 2 cross 2. We are not doing any. If you see, this is a complete block, as one of the audience members asked over here, that we had a convolution followed by an activation and followed by a max pooling. Similarly, we do this just one more time, and remembering the size, we are trying to increase the filter size in each of these iterations. But again, this is not a compulsion. This is just a part of the design of conv. So we can see there are now 64 filters, followed by an activation, followed by a max pooling. And again, we have this particular third layer of convolutional neural network using activation as in ReLU, but we are not performing max pooling just in order to preserve the information that we already have. So I'll go ahead and create this model. And to understand what really model looks like, we can print the model summary over here. So to get a understanding of what the network looks like. So for now, we have the first layer of convolutional neural network that refers to this particular line, where it receives an input of 32 cross 32 cross 3 image sizes, and the output it produces after performing the activation is of size 30 cross 30 cross 32. Now I haven't gone into the mathematics of how connet comes up with this number 30, because it would be much out of scope for this particular presentation of as an intro to connet. But it tries to reduce the if you remember from the presentation, we had a 9 cross 9 image, which was converted to a 7 cross 7 image. A similar technique that is happening over here is the same. We reduce the image size from 32 cross 32 to 30 cross 30, but now we have channels 32 instead of 3 channels was the input. And I won't be talking about the parameters, but parameters are the number of weights that it has to learn and it has to update in each iterations. So you can see from this particular section of summary is what each of these layers do. It These outputs of the particular layer is being input to the max pooling layer, and it produces an output of 15 cross 15 cross 32. And similarly, that is being input to the second layer of convolution, followed by a second layer's max pooling, followed by the third layer of convolutions, so on and so forth. I won't be talking about each of these things in particular detail, but you can see the last output that it created from the third layer of convolution is a 4x4 image with 64 channels or 64 filters as its third dimension. And total number of parameters that you can see over here are 56,000 parameters, which is fairly huge because this particular model has to update and learn 56,000 parameters in order to do the training. And you will see how it is trying to do that. So at the end, if you remember, we had these fully connected layers, which are also known as dense layers, which is just trying to map the class probabilities at the end. So we see the last layer that we have received from the third layer of convolution neural network over here, and we apply a flattened curve over here. So if you remember from the presentation, we are trying to convert each of these feature maps into a one-dimensional array, which is typically referred to as the flatten call function. And we try to use this dense function as a part of a ReLU activation, which will again perform so that none of these negative values really come up. And we apply because we use dense layers of size 10 because we have this 10 class size. So we know each of these one-dimensional arrays of size 10 has to be mapped to these particular 10 values from the labels. So we have this connections of dense layers with a class output size 10. I'll go ahead and create this particular layers too. And to produce a summary of what finally it would look like, we had the output till this over here in the previous section, but followed to that, we applied the flatten function over here, which will just flatten out these particular values, which is 64 cross 4 cross 4. And it will try to map each of these values into a particular dense layered manner. So it tries to convert each of these back into the 64 channels. It will try to remove out all of the channels that were present over here into a particular value, and then it tries to map into these particular 10 class neurons. So we have at the end over here, let me just quickly go back to the first image just in order to understand. Over here, we perform the flatten technique, I would say, followed by dense layer connections. And just imagine over here that we have 10 outputs, so that it's trying to map each of these particular values to particular class labels. In the example presentation, we had just two labels, that is X and O, but over here we have 10 labels. So we are trying to make a map to these particular 10 values. And adding these flatten algorithms, now you can see we are now at a trainable parameters of around 122,000 parameters, which is again fairly huge, but you will see these parameters are fairly small amount of size compared to what deep learning typically does nowadays. So this is a point to be learned over here is we can see these outputs that were trained going through the dense layers, how it looks like. Now we have created this model. Now let's go ahead and provide it the input data set and compile them. I won't be talking much about the optimizers, but Adam is one of the most popularly used optimizers available out there. There is a lot of paper reading that you might have to do in order to choose the best optimizer. But a quick tip from me would be, if you are not sure really which optimizer to use, Adam is one of the most popularly safe to use optimizer. It won't blow up your model. It won't do anything very notorious, but still you will be able to perform all of your um, training in a very reliable fashion. So if you're not sure, go ahead with Adam in general. And as a metric, we are trying to understand the accuracy, as in saying if the image was classified correctly versus not. This is what accuracy means in computer science, saying if the values matched or not, yes or no. And model.compile does, it puts up this model together. It labels these metric values, and it tries to compile this particular model. And model.fit is the part, the beauty of this particular deep learning is where we perform the training. So we provide the training images, training labels. number of epochs that really varies from person to person. But just for the sake of this demonstration, I'm keeping the number to 10 in order to not let you guys wait a lot. But the epoch number can really go ahead in order to achieve better accuracies. And we'll be using as a validation set the test images on which we will be testing our accuracies. So I'll just quickly go ahead and run this particular cell in order to see what it looks like. So as you can see, the training has really started over here, and we see each of these batches of 1500 images is created, and it tries to do training in general. And one thing that we as programmers should be really concerned and really observing about is these values that are really created at each of these epochs. So as you can see in this particular model that I created, the accuracy values are really increasing in a very consistent manner, which is a very requirement, nicey thing that all of us should be really looking forward to is a model shouldn't be really going down after a lot of number of epochs. A small jump towards the decrease of accuracy is fine, but it shouldn't be fluctuating a lot. It should be consistent enough to not increase or maybe increase, but it shouldn't be decreasing in a consistent manner. If it is decreasing, you need to change your hyperparameters of the model at certain step, or maybe just use a different data set because the data set might be corrupt. So what we did over here is 10 epochs, and we performed the training over here. And at the end, we got an accuracy of 78, which we see there is a consistent amount of increase in these accuracies. And we stumbled onto 78% accuracy from the training data set, which is a very important thing to notice. And similarly for validation that we see, it started from 54, and over here it has stumbled to around 70 or something. Now let's see the plot of these particular accuracy values, what it looked like. So as I said, the accuracies for training and validation should increase in an overall fashion. It shouldn't go the other way around. It shouldn't go down the valley. That is what a model is learning wrong things that we can conclude over here. But overall, as you can see, both of these values are increasing. Small spikes are fine, but it should overall learn something really valuable. So this is a quick test of to understand whatever we did is correct or not. But so far, so we are good. Now let's go ahead and test the testing accuracy over here. That seems to be fine enough. It came out around 70% on the testing data set, which is highly consistent with the validation accuracy because it was around 70 something. And we got the same number over here, which is consistent with the training accuracies. So this is what a normal convolutional neural network would look like. So we started off by understanding what libraries to use, how to go on with normalizing the data sets, how to go on looking at these class labels to make sure which images we are really working with. A very simple layer. Now, again, as you can see, the 70% accuracy is not a very really great number. The reason is just for the sake of demonstration, I have used a very small amount of layers over here with a fairly small amount of filter size. But that is just for the sake of demonstration. If I were to tune these particular layers or maybe increase few layers and not perform max pooling or something, it might result in a better accuracy. But just for the sake of keeping this model simple and sweet, I have used only 3 layers over here. And these are the model summaries that any one of you, if this code should be available to all of you in order for any one of you guys to rerun or do some kind of tests. But you should be courageous enough to at least change these parameters in layers and just walk around and see what it looks like. So this is what it would seem like. um, so far, that's all from my end for the demonstration. I'll open and allow you guys to talk more about if you guys have any specific doubts regarding this implementation. So I'll be open, but so far from my end, I'm done. But I'll be on the call in just in case any one of you has doubts or concerns about implementation or in general the theory of convolutional neural networks. So yeah. Advait, are we doing good on time?
Yep, you're doing good. Does anyone have any questions for Jay? You can go ahead and ask it through the chat, or you can speak it out loud, however you would like to.
And even in case somebody has doubts after the implementation, feel free to reach out to any one of us or uh, uh, like to me in general. I'll be happy to answer of any of these questions. But I'll really encourage everyone to just play along these particular codes. I have kept this particular code base as a very simple in order for you to play around. So yeah, even if after this call, if somebody has any doubts, feel free to reach out to me or any one of AI Club members.
Yep. And if
Um,
you guys are interested in watching this workshop again, it will be posted on our YouTube channel, which is the links in the chat. So feel free to check that out. And Jay's workshop will be on there soon.
and I have a question. You said the accuracy of the model would increase if you reduce the number of pooling sessions in between.
Hmm. Hmm.
Uh, so the more convolution blocks we run, uh, it's going to be more accurate. Why is that?
Right, right. Because if you see these feature maps, let me just pull back to the original presentation. Let me just go ahead and so, are you able to see the screen?
Yeah.
Yeah. So if you see each of these images at the end, it learns certain amount of parameters. So over here, it tries to see that this particular pattern is being consistent, and hence it tries to find certain amount of things. So yes, in a way, by stacking more amount of convolution layers, it really finds much more deeper understanding or maybe deeper information in the images. But if you perform pooling by a very huge number, it will try to decrease the information size present in each of these poolings. So you need to be really careful of how much pooling that you are using, because pooling is in a way you are trying to reduce the information size. So yes, but you need to be really careful by while stacking your convolution layers, so that you are not losing out on the information, but also trying to learn these models, learning the information. But yes, as a thumb of rule, better the more the layers, more the accuracies, but it is not a magical wand that will just give you more accuracies. You need to be careful that how much layers you are stacking. And computation really increases by an exponential level. So having infinite number of layers is really impractical, or more number of layers is highly impractical. So yes, there is a sweet spot in between them. But yes, more layers would increase the accuracy values in general.
And if we were to do two convolution blocks simultaneously, at the end of the first block, we get an output. For example, the blue one on the right side. So would that become the input for the next convolution block?
Right. So
And
so
if we were to
yeah.
do that, wouldn't it automatically reduce the size? It's like
Yes,
pooling on its own, but in larger steps.
yes. So yes, each of these let me pull out an image, other one that is really easy for each one of us to understand. So each of these, when you stack each of these layers, the output of convolution block one is the input to the convolution block two. And yes, it receives a downsampled image of output of the original input to the second layer of the convolution. So yes, to answer your question, yes, you are right. You are correct.
Thank you. That's
Mhm.
it.
Jay, there's a question in the chat.
Right. So the question is, what are some practical ways that you have utilized convolution neural networks? Any specific projects? So yes, I have used convolution neural networks in lots and lots of application, from starting from understanding facial recognition systems in videos. So it will try to do a real-time based understanding of who the person is in particular convolution neural network and how it really looks like. Now that you guys have an understanding of what convnets really look like, is you have this training that you do on a certain set of data sets. So let's say over here in this particular call, we have what around 10 to 15 people, and if I train each of these faces in particular data set in convolution neural network, the network knows what how I look like, what Advait looks like, what Eva looks like, and it will try to now use this particular knowledge, and it will try to see patterns. So if I give a particular video of Advait speaking something, it will try to see and it will try to look for patterns within that particular video frame in a consistent manner, and it will do a face recognition system and will say that, hey, Advait is present in this particular video. And some other cool application that I'm currently using and my current research work is much more focused on is to understand how brain imaging looks like. So you have this very rich data set of MRI data sets, which is of a much huge size than what we particularly take photos on maybe iPhone or any kind of mobile phones that we have. And we are trying to see how brain imaging in case of Alzheimer's. So Alzheimer's is a kind of disease where we have this certain regions of the brains that are deprecated or maybe degenerated, that they say in a medical terms. But doctors are typically not able to see these small changes and small degeneration techniques over here. So convolution neural networks are highly precise. If you tune the knobs, if you remember the term that I used, these knobs, if I make convolution neural network really specific to very small details of the brain, it will try to see if these kind of degenerated cells are really present over there. And so basically if I input a particular MRI scan of a patient over here, convolution neural network can really say that, hey, this person maybe suffers from Alzheimer's disease in the next 5 years, which is highly crucial information to a doctor, because if a doctor knows that this person might suffer from Alzheimer's in the next five disease, he can really give some prescriptive medicine, or it leads to drug discovery. So this is how I have been using, but they are much more advanced version of this particular convolution neural networks. They are not just convnets, but I'm using convnets as a tool to do that. There are lots of other techniques that is much more out of the scope for this presentation, but convnets is one of these building blocks of those architectures, and it uses convnets as a tool to achieve that pattern matching knowledge acquisition. So but again, there are tons of applications: self-driving cars, securities, uh, your iPhone's camera system, how it unlocks your iPhone. These are the applications that are like highly robust, highly popular, highly fast, and really useful in everyday applications. I hope that answers your question. Like, does that answer your question? Awesome. All right.
Alrighty, thank you so much, Jay, for giving that amazing presentation. Like I said before, this will be posted on our YouTube channel. So if you guys would like to watch Jay's presentation again, you're more than welcome to. It'll be up and on there by this weekend. Apart from that, you guys are free to go. Thank you all for coming, and thank you, Jay, again for presenting.
Sure. Thank you very much to you guys.